What specific problem does RACTD aim to solve in the context of offline reinforcement learning, and how does it differ from existing methods?
RACTD aims to address the challenge of effectively utilizing suboptimal datasets in offline reinforcement learning, RL, by integrating reward optimization directly into the consistency distillation process. Unlike existing methods that either rely on behavior cloning, which struggles with non-expert data, or actor-critic frameworks that complicate training with multiple networks and sensitive hyperparameters, RACTD simplifies the training process by allowing the reward model to be trained independently from the teacher diffusion model. This approach enables the student model to sample actions that yield higher rewards, steering it towards optimal trajectories while maintaining a single-step generation process. Additionally, RACTD achieves superior performance and substantial sampling efficiency, demonstrating an 8.7% improvement over state-of-the-art methods and a 142-fold reduction in sampling time. Overall, RACTD's unique integration of reward objectives into the distillation process distinguishes it from traditional methods, enhancing its effectiveness in offline RL scenarios.
How does the proposed method RACTD work? Illustrate the key steps of the algorithm, including the role of the teacher and student models, as well as the integration of the reward optimization process.
The proposed method RACTD, Reward-Aware Consistency Trajectory Distillation, operates by integrating reward optimization into the consistency distillation process, leveraging a pre-trained unconditional diffusion policy as the teacher model. The key steps begin with the teacher model, which captures diverse behavior patterns through a many-step diffusion process. The student model is then trained to emulate this process in a single step, utilizing a consistency trajectory distillation approach that aligns predictions across different time intervals. Importantly, RACTD incorporates a reward model, which is trained independently, to guide the student model towards actions that yield higher rewards, effectively steering it to select optimal trajectories from the multimodal distributions learned by the teacher. This decoupled training simplifies the process, allowing for efficient single-step generation while achieving superior performance and substantial sampling efficiency compared to existing methods.
Can you provide a simple yet detailed example that exemplifies the inner workings of the RACTD algorithm? Explain the process from input to output using an example scenario.
The RACTD algorithm operates by integrating reward optimization into the consistency trajectory distillation process, enhancing decision-making in offline reinforcement learning. For example, consider a scenario where an agent is learning to navigate a maze, like Maze 2D, using a dataset that includes both expert and suboptimal actions. Initially, the agent uses a pre-trained unconditional diffusion policy, the teacher model, to capture diverse behavior patterns from the dataset. During the distillation process, the student model generates a sequence of actions based on a fixed-length sequence of observed states, while simultaneously evaluating these actions using a pre-trained reward model that predicts the expected future rewards. As the student model samples actions, it focuses on those that yield higher rewards, effectively steering its trajectory towards optimal paths identified by the teacher model. The final output is a single-step action sequence that maximizes the expected cumulative reward, allowing the agent to navigate the maze efficiently. This process not only simplifies training by decoupling the reward model from the teacher, but also significantly accelerates sampling, achieving up to a 142-fold reduction in sampling time compared to traditional methods.
What unique benefits does RACTD offer over traditional actor-critic methods and existing diffusion-based acceleration techniques? Discuss in terms of performance, efficiency, and training processes.
RACTD offers several unique benefits over traditional actor-critic methods and existing diffusion-based acceleration techniques. Firstly, in terms of performance, RACTD achieves an 8.7% improvement over the state-of-the-art while maintaining the ability to sample efficiently with a single-step generation process, unlike actor-critic methods that require concurrent training of multiple networks, which can lead to instability and complexity. Secondly, RACTD significantly enhances efficiency by reducing the number of necessary denoising steps, achieving up to a 142-fold reduction in sampling time compared to the teacher model, while traditional methods often rely on multiple function evaluations that slow down the process. Lastly, RACTD simplifies the training process by allowing decoupled training of the reward model from the teacher diffusion model, avoiding the complexities associated with multi-network optimization and noise-aware training required in actor-critic frameworks. This streamlined approach not only stabilizes training, but also enables flexible integration of different reward models, enhancing overall adaptability and performance in offline reinforcement learning scenarios.
Describe the experimental setup used to validate RACTD. What datasets were utilized for testing, and what specific metrics were employed to demonstrate the method's effectiveness?
The experimental setup to validate RACTD involved testing on the D4RL GIM MuJoCo benchmark, which includes environments such as Hopper, Walker 2D, and Half Cheetah, characterized by varying quality data, medium replay, medium expert. The evaluation employed online model selection, using the best performing checkpoint observed during training, and results were reported as the mean and standard error over 100 planning seeds. Additionally, RACTD was tested on the D4RL Maze 2D environment, a long-horizon planning task where the performance was assessed based on the ability to reach goals in static environments. The effectiveness of RACTD was demonstrated through metrics such as overall average score improvements, achieving an 8.7% enhancement over the state-of-the-art and a 142-fold reduction in sampling time, highlighting both performance and sampling efficiency.
What limitations have you identified in the RACTD approach? Discuss any potential drawbacks regarding its scalability, generalizability, or reliance on the quality of the training dataset.
The RACTD approach, while innovative, has some limitations that could impact its scalability and generalizability. One potential drawback is its reliance on the quality of the training dataset. The method may struggle with suboptimal data, as it is designed to favor high-reward modes, which could lead to discarding valuable behaviors present in lower-quality data. This reliance on the dataset quality may limit the model's ability to generalize effectively to novel scenarios, particularly if the training data does not encompass a diverse range of behaviors. Additionally, while RACTD simplifies training by decoupling components, the performance gains from the reward-aware student model may not scale linearly with the complexity of the tasks, as indicated by the observation that increasing the number of denoising steps does not yield proportional improvements. Lastly, the method's performance is contingent on the teacher model's ability to capture a comprehensive range of behavioral patterns, which could be a limiting factor if the teacher is trained on a dataset that lacks diversity.